So far, we have talked about electric force quantitatively. Now, it's time to get quantitative with Coulomb's law. Charles Coulomb was able to precisely measure the electric force between objects using a device he invented called the torsion balance. The force between two charged spheres would cause a suspended fiber to twist. By measuring the angle of this twist, he could get a quantitative measure of the force. In his analysis, we often model the charged object as point charges, meaning particle with charge but no size. Mathematically, we write Coulomb's law as shown. The magnitude of the force F equals the Coulomb's constant Ke times the magnitude of the product of the charges divided by the square of the distance r in SI unit. The Coulomb constant K is approximately 8.99 times 10 to the 9th power Newton meters squared per Coulomb squared. The SI unit of charge is a Coulomb. It's critical to remember that force is a vector. This diagram shows two like charges, Q1 and Q2, which produce a repulsive force between them. The force on Q1, labeled F21, points directly away from Q2. The force on Q2, labeled F12, points directly away from Q1. As per Coulomb's third law, these forces are equal in magnitude and opposite in direction. Similarly, if we have two unlike charges, they produce an attractive force. The force on Q1 is directed towards Q2, and the force on Q2 is directed towards Q1. Again, the forces are equal in magnitude and opposite in direction. The electric force is a field force. This means it can act over a distance without any physical contact between the objects, just like gravity. While there are similarities between electrical and gravitational force, there are also very important differences. Let's compare them. Both the electric force and the gravitational force are inverse square laws, and their mathematical form are almost identical. However, gravitational forces are always attractive, while electric forces can be either attractive or repulsive. The most significant difference is their strength. On an atomic scale, the electric force is tremendously stronger than the gravitational force. What if we have more than two charges? The answer is given by superposition principle. It states that the total or resultant force on any single charge is simply the vector sum of the forces exerted on it by all the other individual charges. You calculate each force one by one using Coulomb's law and then add them all together as vectors. Here is a visual example. To find the total force on charge Q3, we first calculate the force exerted by Q1 on Q3. We call it F13. Then we calculate the force exerted by Q2 on Q3, which we call F23. The total force on Q3 is the vector sum of F13 and F23.